In this video, I want to do a little bit more with probability involving permutations and combinations. And as I've mentioned before, at the heart of probability is counting. And the majority of the work involved in calculating probabilities will be counting. So in this example, or in this worksheet, I'm going to go through a few examples focusing on the counting processes that we've discussed, namely the fundamental counting rule, permutations, and combinations. So let's look at a problem that we've already done using the fundamental counting principle, or the fundamental counting rule. How many license plates are possible if each plate consists of 3 letters followed by 3 numbers if license plates have no repeated letters or numbers? So that's important. All right, so if we look up here at the top, this bulleted list, if these 3 criteria are met, there are n different items available. If we're talking about letters, there would be 26 available, so n equals 26. Or if we're talking about numbers, 1-digit numbers, then if we look at the digits 0 through 9, then there's 10 available numbers to choose from. And we're selecting R of those items. So R is the size of the group that we're choosing from the larger group. So with the letters, if we have n equals 26 or 26 letters to choose from, R in this case, in this example, would be 3. And if we're choosing 3 numbers out of 10 options, then n would be 10 and R would be 3 as well. And we consider rearrangements of the same items to be different if the sequences are different. All right, so order matters. If you have to enter your license plate and you swap 2 of the letters, or 2 of the characters, it's not actually your license plate. It's a different license plate. So order matters and no repeat. So if these 3 criteria are met, we call this a permutation. So the number of permutations is given by this formula over here on the right. Okay, so back to the license plate. How many license plates are possible? Well, we've done this problem previously using the fundamental counting rule. And the fundamental counting rule says we look at each selection individually. So each of the 3 letters individually and each of the 3 numbers individually. And we go character by character and look at how many choices we have at each step in the sequence. This would be a 6-step sequence. Our license plate, let me scroll down a little bit. Our license plate has 3 letters followed by 3 numbers. So letter number 1, letter number 2, letter number 3, number 1, number 2, number 3. So that's a 6-step sequence. Now if we look at, for that first letter, how many options do we have to choose that first letter? Well, there's 26 letters to choose from, so 26. And once we've chosen one letter, if repeats are not allowed, right now we have 25 letters to choose from for that second character in the license plate, or that second letter. And once we've chosen 2 letters, we're down to 24 choices. And now for that first number, we have the digits 0 through 9. Again, we have 10 choices. So for that first number, there's 10 options there. Once we've chosen one of those 10, and repeats are not allowed, so one of them's gone, we're down to 9 choices left. And then for that last number, we're down to 8 choices. So the fundamental counting rule says look at each step in the sequence, count how many ways that step can be done, and then multiply each of those numbers. And that will give you the total number of ways the entire process can be done. So 26 times 25 times 24 times 10 times 9, excuse me, times 8. And if you put that into a calculator, you'll have to take my word for it, but you could pause the video and double check this, but you get 11,232,000 possible license plates. So this is solving the problem using the fundamental counting rule. Now, if we look at this problem in a slightly different way, instead of saying choose the first letter, then the second letter, then the third letter, and then the first number, second number, third number, we could look at this problem in terms of how many ways could we choose those three letters. So we could look at it as basically as a two-step process. Choose the letters and then choose the numbers. And this is where we could use permutations. Permutations is the number of ways we could select a group of objects from a larger group of objects. Remember, the important criteria here are no repeats and order matters. Order matters. So how many ways could we choose three letters out of the 26? So n, again, n would be 26, r would be 3. All right, so that's 26 permutation 3. Now we have to calculate this, but this is just our symbol for the number of ways you could select 3 objects out of 26 if order matters and there's no repeats. And then for the 3 numbers, that would be 10, because we have a group of 10 numbers to choose from, 10 permutation 3. And now to calculate each of these, now I'm going to scroll up for a moment. Here's the formula for that. N factorial divided by n minus r factorial. Right, so that's the formula that we would be using to calculate each of these permutations. So let's say, there we go. So this first permutation would be 26 factorial divided by 26 minus 3, which would be 23, factorial. And the fundamental counting rule says we multiply these two numbers. So we would multiply by plugging the 10 and the 3 into that formula. So n permutation r, just recopy the formula down here, is n factorial divided by n minus r factorial. Okay, so that would be 10 factorial divided by 10 minus 3 factorial. So as I've mentioned before, I don't think it's necessary that you crank these calculations out by hand or even with a calculator. I like Desmos for a quick and efficient way to, let's see, Desmos is right here, a quick and efficient way to calculate these permutations. So in Desmos, we will type in, if we want Desmos to do a permutation for us, we will type in N capital P and then R. Ooh. All right, sorry about that. We would type in lowercase n, capital P, lowercase r, so NPR. That's telling Desmos you want to calculate a permutation, and then in parentheses tell Desmos what is the n and what is the r. So 26 is the n and 3 is the r, so 26 comma 3. So this, what I just typed into Desmos, this is asking Desmos to calculate the permutation 26 permutation 3. And so we get 15,600. And that second one for the 3 numbers out of 10, so choosing 3 objects out of 10 would be n permutation r, NPR, 10 comma 3. And so there's 720 ways to choose those 3 numbers. Okay, so we could say equals 15,000 and 600. That's just the, this is basically saying there's 15,600 ways to pick 3 letters out of 26. And then for the numbers, we got 720. So there's 720 different ways just to pick 3 numbers out of 10. And the fundamental counting rule says we multiply those two together. Again, I've done this previously, so if we multiply those two together, we get 11,232,000. And that's the same result as we got previously using the fundamental counting rule. So if I scroll up, maybe if I could zoom in to see both at once. So this is basically two ways of doing the same problem. Okay, so the fundamental counting rule is not completely separate or mutually exclusive from the permutation rule. There's situations where you could use both. All right, so moving on to the other counting technique, the combination rule. So combination rule, very similar to the permutation rule, with the one difference being order doesn't matter. So we consider rearrangements of the same items to be the same. So ABC, CBA would be considered the same combination of letters. Or combinations are groups. So ABC, CBA, the same group of three letters. So if these three criteria are met, here's the formula for the combination, or the number of combinations of objects possible. You see, it's similar to the permutation formula. We basically have the permutation formula in there with this extra r factorial on the bottom. All right, so to show the combination rule in action, I want to look at a problem involving a deck of cards. So the question here is, which 5-card poker hand should win? A hand containing 4 of a kind, or a hand containing 5 cards of the same suit, which is called a flush. Okay, so we have two hands. We have a hand containing 4 of a kind, so like 4 2s or 4 7s or 4 jacks, and a hand containing 5 cards of the same suit, which we call a flush. So those are the two different hands. So we want to count how many ways each one of those hands is possible. So let's start with 4 of a kind. Okay, so how many ways, and we're not going to need the combination rule for this one because it's a small number of options. So how many hands contain 4 of a kind? Well, there's not that many. In this case, we could basically list them all out. So basically we're choosing 4 cards for the 4 of a kind and then the 5th card. So how many ways can we do this? Well, again, this is a fundamental counting rule problem. We could look at how many ways we could choose those first 4, and then how many ways could we choose that 5th card? Well, 4 of a kind, there's not that many of them. There could be 4 aces in a hand. Right? There could be 4 2s, 4 3s, 4 4s, 4 5s, 4 6s, 4 7s, 4 8s, 4 9s, 4 10s. Oop, not 1,000. 4 10s, 10, 10, 10, 10. 4 jacks, 4 queens, or 4 kings. So there could be one group of 4 for each type of card. There's 13 of them. So there's 13 different 4 of a kinds. That accounts for 4 cards. And so once you have 4 of a kind, how many options do you have left for card number 5? Well, there's 52 cards in the deck. 4 of them are gone because there's a 4 of a kind that came first. So that leaves you 48 cards left in the deck. So 13 times 48. Let's do that down here. 13 times 48 equals, and I use a calculator for this. Feel free again to pause the video and just double check my work, but I get 624. So there's 624 different 5-card combinations that have 4 of the same card. Okay, so that's 4 of a kind. Let's move on to 5 cards of the same suit. How many hands contain 5 cards of the same suit? Well, there's 4 suits in the deck, right? There's hearts, there's diamonds, there's spades, and there's clubs. All right, so the number of 5 card hands with 5 hearts should be the same as the number of hands with 5 diamonds or with 5 spades or with 5 clubs. So let's focus in on one of those first. Let's say, how many hands just contain, for example, 5 hearts? So there's only hearts in the hand. There's no other type of card. No diamonds, no spades, and no clubs. So let's look at 5 hearts. Well, there's more than 5 hearts in the deck, right? There's 13 of them. You're picking 5 of them. So how many ways could you pick 5 cards out of 13 available cards? So there's 13 hearts in the deck. We're picking 5 of them. So that's a combination. 13 combination 5. Out of the 13 cards in the deck that are hearts, or of that suit hearts, we're picking 5 of them. So according to that formula, that would be 13 factorial divided by 13 minus 5 factorial multiplied on the bottom by 5 factorial. And 13 minus 5 is 8, so that would be 13 factorial divided by 8 factorial times 5 factorial. And if you wanted to do this by hand, well, if you think about what a factorial is, 13 factorial means you're multiplying the numbers, all the numbers from 13 down to 1. So times 10, 9, 8, 7, 6, 5, 4, 3, times 2, times 1. That's what we mean by 13 factorial. And then the 8 factorial would be 8 times 7 times 6 times 5 times 4, 3, 2, and 1. So there's the 8 factorial on the bottom, and then there's another 5 factorial. So 5 times 4 times 3 times 2 times 1. And then since we have a fraction here, there's common multiples on the top and the bottom. So on the top, you see the numbers 1 through 8 multiplied together. So that 1 through 8 on the top, that cancels the 1 through 8 on the bottom. So we have 13 times 12 times 11 times 10 times 9. That's what's left on top, divided by 5 times 4 times 3 times 2 times 1. We can go a little further even and say, okay, on the bottom, 5 times 2 is 10. So the 5 and the 2 on the bottom will cancel with the 10 on the top. 12 divided by 4 is 3. So the 12 over 4 becomes a 3. 9 divided by 3 is 3 as well. So that 9 on the top, 3 on the bottom becomes a 3. So we're left with 13 times 3 times 11 times 3. Which, if we put this into a calculator, we get 1,287. Okay, so this is, I just wanted to throw this in there so you could see how to calculate a combination by hand. But what I want to do is go straight from here, what we want to do, down to here, the answer. So again, using Desmos for that, to calculate the combination 13 and 5, or 13 combination 5, you would type into Desmos N capital C, excuse me, N capital C R, and then in parentheses the N and the C that you want to use. So 13 comma 5. And so if you pull up Desmos and type that in, it should give us the 1287 without doing any of that work by hand. So let's see, lowercase n, capital C, lowercase r. So we're telling Desmos we want to use the combination formula, in parentheses 13 for the n, 5 for the r, and you see, boom, there's our 1287. All right, so that doing the combination by hand isn't necessary because we have ways to do that quickly and efficiently. All right, so what is 1,287? Well, that's just what we figured out was only for 5 cards containing all hearts. So there's 1,287 hands with 5 hearts, which means there's 1,287 hands with 5 diamonds, 1,287 hands with 5 spades, and 1,287 hands with 5 clubs. So if we say 5 cards of the same suit, well, there's 4 different suits, so 4 times 1,287. If we multiply those two numbers, we get 5,148. Okay, so what have we seen so far? Well, we've counted the number of ways you could have 4 of a kind. That's 624. We've counted the number of ways you could have a flush or 5 cards of the same suit. That's 5,148. So let's copy those answers down because now we're going to work with them. So now let's look at the probabilities. What is the probability of each one of these hands? Well, most of the work is done already. So 4 of a kind, there were 624 of those, and for a flush or 5 cards of the same suit, there were 5,148 of those. So now calculate the probability of each of these. What is the probability of being dealt a hand with 4 of a kind, and what is the probability of being dealt a hand with a flush? So our definition of probability in the classical sense is the number of simple ways the outcome A can happen. So we have that already. If our outcome is 4 of a kind, we've counted 624 ways to do that. And if our outcome is a flush or 5 cards of the same suit, we've counted 5,148 ways to do that. So that's the numerator of this fraction. So now we need the number of possible simple outcomes from the experiment. And the experiment in this case is choosing 5 objects out of 52. 5 cards out of the deck. Order doesn't matter. So it's again a combination. So forget about 4 of a kind, forget about flush. Just how many different ways can you pick 5 cards? That will be the sample space, the total number of different possible simple outcomes of our experiment, or in this case, how many 5-card hands are possible. All right, so in this case, the number of objects is now the entire deck, 52. The number of hands, or the number of cards we're choosing is 5. There's no repeats. I mean, there's no repeats because there's no card that's repeated in the deck. There are no 2 copies of the same card, so there's no repeats. And order doesn't matter. If you choose 5 cards out of the deck, hold them in your hand, rearrange the order, it's still the same group of 5 cards. All right, keyword here is group. So that tells us we're dealing with a combination. So we're trying to calculate N combination R. And we could pop over to Desmos for that. And then just instead of 13 and 5, so in the last example, we were looking at just the hearts, just the 13 hearts in the deck. In this case, we're looking at the entire deck. So N combination R, and out of 52 objects, we are choosing 5 of them. And so we see there's 2,598,960 possible 5-card combinations. Or if you play poker, there's 2,598,960 possible 5-card poker hands. So the counting is done, and the probability is just a small step after that. The number of simple ways your outcome could happen. So if we want the probability, so let's get rid of this highlighting. Let's look at the probability of 4 of a kind. Right? The number of simple ways that could happen is 624. The total number of possible simple outcomes from your experiment, that's the 2,598,960. So to calculate this probability, we take those two numbers and we divide them. We take 624, the number of ways our outcome can happen, or our event could happen, divided by the total number of ways the experiment could play out. So the probability of being dealt 4 of a kind let's see. So the probability of being dealt 4 of a kind should be the 624 divided by 2,598,960. And if we pop that into a calculator, and again, you could pause and double check my calculations, but I get 0.000, and I'll go to 3 significant digits, so 0.00240. And if we look at the probability of being dealt a flush, or 5 cards of the same suit, so now instead of the 624, we're looking at the 5,148. So now the number of ways our outcome could happen is the 5,148. The number of ways our experiment could play out is the 2,598,960. So the probability of being dealt a flush, we would divide those two numbers. So probability of a flush, 5,148 divided by 2,598,960, and according to my calculator, rounded to 3 significant digits, I get 0.00198. If we convert these to percentages, so move the decimal point 2 places to the right, that's about, for the probability of 4 of a kind, that's about 0.02%. So a very low probability, way less than 1% of the time. Yeah, well, again, we're rounding this, but 0.02% is a very rare hand. And if we convert the probability of a flush to a percentage, again, move the decimal point 2 places to the right, and we can round that. Well, that's about 0.2%. So that's 10 times more likely. So what this is saying, these probabilities, a flush happens 10 times more often than 4 of a kind. So which hand should be the winning hand? Well, the one that's more rare, the one that's harder to get, or the one that's happening less often. So the winning hand should certainly be 4 of a kind, and that's specifically because it has a lower probability. Lower chance of happening. So if you play poker, even if you don't, the reason the rules are what they are, the reason a flush loses to 4 of a kind, or a 4 of a kind beats a flush, is because of the probabilities of each of those things happening. Probability of a flush, 10 times more than probability of a 4 of a kind. Okay, so that does it for this worksheet. In terms of just in general, choosing when to use a permutation, which we did first, or a combination, which we did second, in both cases, well, let me go down a little bit here. In both cases, repeats were not allowed. No repeats. If order matters, passwords, IDs, social security numbers, phone numbers, license plates, things like that, then we're looking at a permutation. If order doesn't matter, we're talking about groups or teams or collections. So order doesn't matter, then we're talking about a combination. All right, that does it for this worksheet. I hope this was helpful.